The next application we're going to take a look at is particle motion. I know we've already done a little bit of this, but we really just kind of saw how to create position, velocity, acceleration formulas. What we now need to do is analyze the motion of the particle way more than we did before. Before we go on, I'm going to show you a quick video clip of a particle moving back and forth. So take a look at this particle that we have over here. I'm going to push the run button and watch it move. In some places moving to the left, in other places moving to the right. It's going faster in some places, slower in other places. We could see sometimes when it was speeding up, sometimes when it was slowing down. There seemed to be a furthest left position it hit, a furthest right position it hit. We're going to see how to analyze all this motion using some calculus. And hopefully you saw that there were times when the particle was moving to the left, times when it was moving to the right, times when it was kind of slowing down, times when it was speeding up. There was a furthest left point it reached, furthest right point it reached, I think, we'll see. And I want to try to analyze all this stuff. For starters, so basically what we're going to do in this video is just get all the notes down of different things that we can figure out. Then the next two videos, or maybe just next video, I'm not totally sure how I'm going to do that, we'll go through some examples. S of t is our position. V of t, our velocity, we can find by doing the derivative of position. This is nothing new. And then A of t, which is the derivative of velocity, or the second derivative of position. That's our acceleration. We've already talked about these three things, but get those down in your notes anyhow. Our particle is at rest when what is true? When the time is zero, when the position is zero, when the velocity is zero, or when the acceleration is zero? When our velocity is zero, the particle is at rest. We are at rest when the velocity equals zero. Now, we've talked before about what velocity is. Velocity is speed, but with a direction associated with it. We have two directions, left and right. And we're going to determine what direction we're going just based on the sign of our velocity. Our particle will be moving to the right when our velocity is greater than zero. And similarly, and I'll give you a moment to write, our particle is moving to the left when my velocity is less than zero. Take a moment, copy those down. Next, my velocity is increasing when, well, for anything to be increasing, its derivative must be positive. So the velocity is increasing when what must be true? When its derivative, which is acceleration, is positive. My velocity is decreasing. Anything is decreasing when its derivative is negative. The derivative of velocity is acceleration, so when A of t is less than zero. Take a moment, get those copied down. speed. Speed is like velocity, but without the direction. Our directions are either just positive or negative, left, right. How do we take the velocity and just ignore the sign? We're going to take the absolute value. Speed is the absolute value of velocity. Next, our particle is speeding up, also sometimes referred to as speed is increasing. When? Our particle is speeding up. Its speed is increasing when, well, first of all, this is different than talking about the velocity of a particle increasing. If the velocity is increasing, that means our velocity could go from 4 to 5 to 6 to 8 to 10, which definitely means it's speeding up. But if our velocity is increasing, that could also mean the velocity is going from negative 12 to negative 10 to negative 8 to negative 6. The velocity is increasing. Those values are increasing. But as we go from negative 12 to negative 10 to negative 7 to negative 5, our particle is actually going to be slowing down. So we're going to make a distinction between velocity increasing and speed increasing. Speed increasing, particle speeding up truly when it's getting faster and faster and faster. That's going to be true when the velocity and acceleration have the same sign. Our particle will be speeding up if the velocity and acceleration have the same sign. Similarly, and then I'll demonstrate this in just a moment, our particle will be slowing down, or its speed is decreasing when v of t and a of t have opposite signs. Take a moment, write that down, and then we're going to kind of process this. Okay, we're speeding up when velocity and acceleration have the same sign. So when the velocity is positive and the acceleration is positive. So when the velocity is positive and the velocity is increasing. If the velocity is positive, that means I'm going to the right. So we're going to take a look at my friend, the lemur over here, and he's moving to the right. And if the acceleration is positive and the velocity is positive, that means when he's going to the right, his velocity is 1, it's 3, it's 5, it's 7, he's moving faster and faster in that direction. That wasn't a great demonstration. Let me show you again. If the velocity is positive, so I'm moving to the right, and the velocity is increasing, his velocity is 1, is 3, is 5, is 7, and he's moving faster and faster that way. Similarly, if the velocity is negative, that means we're going to the left. And if the acceleration is negative, that means the velocity is decreasing. So I'm moving with a velocity of negative 1, negative 2, negative 3, negative 5, negative. I'm moving faster and faster in that direction. As for slowing down, velocity and acceleration have opposite signs. That would be like saying we're moving to the right, velocity is positive, but the velocity is decreasing, the acceleration is negative. So I'm moving at a speed of 5 miles per hour, 4 miles per hour, 3 miles per hour, 1 mile per hour. Or if I'm going to the left, I could have a velocity that is negative and acceleration that's positive. So my velocity is negative and it's increasing. I'm going negative 10 miles per hour, negative 5 miles per hour, negative 2 miles per hour, slower and slower in that direction. I'm not sure how much the lemur helped. It's easier when I can just like walk in front of the class faster and slower and whatever. But hopefully you get a little bit of an idea, speeding up versus slowing down. Very lucky that I just happened to have a lemur lying around my desk. Next, I think that's what it was anyhow. I'm not totally sure. We might be asked when the particle is furthest to the left or furthest to the right. Furthest left or furthest to the right? Well, we're going to find the absolute maximum or minimum position of the particle. Furthest left, furthest right, that's the absolute maximum or minimum position. And we're going to use the candidates test. Let's get that one copied down. Two more. Our velocity is the derivative of position. That's our instantaneous velocity, but sometimes we might be asked for the average velocity over some interval. Our average velocity is going to equal the change in position over the change in time. This is our change in position over our change in time. Also sort of looks like our mean value theorem stuff. This is our slope of the secant line, and some of the slope of the tangent line has to equal that. Our average velocity change in position over the change in time. We might also be asked for the average acceleration over a closed interval. And that's going to work in a similar way. Average acceleration is our change in velocity over our change in time. I'm going to make the video pause for a moment. So hopefully all that stuff is copied down. And we are, in the next video, going to take a look at a couple of examples of this.